Good evening, everyone, and welcome. It is my pleasure to see so many of you gathered here in Swift Hall for one of the Divinity School's most enduring and beloved traditions, the Nuveen Lecture. The Nuveen Lecture is named for John Nuveen, who was one of Chicago's most influential business leaders. He was an active civil and cultural leader with ties to many educational institutions, including our own University of Chicago. Here he served as a member of the Board of Trustees. He was chair of the university's Alumni Association, and he was a trustee of the Baptist Theological Union, which helped to establish the Nuveen Lecture in his name in 1972. And just parenthetically, I connect this lecture also to another generous donor, Jeff Wolf, and this is connected with a larger program related to religion, science, and technology, which Daniel Holtz's work connects to most beautifully. The Nuveen Lecture has long served as a meeting ground between theology and the sciences, faith and reason, the human and the cosmic. Tonight, that conversation continues in extraordinary fashion with our speaker, Professor Daniel Holtz. Professor Holtz is a physicist, an astronomer, and cosmologist here at the University of Chicago. He is professor of physics, astronomy, and astrophysics, a member of the Enrico Fermi Institute, and the founder and director of the Existential Risk Laboratory, or as we all now know, XLab, which is doing amazing work to prevent the end of the world. His research explores gravitational waves, black holes, and the deep structure of the universe itself. He is also known for his role with the Bulletin of the Atomic Scientists, where Professor Holtz serves on the Science and Security Board, the group that sets the time of the Doomsday Clock, which, as of this year, stands at 89 seconds to midnight. The title of Professor Holtz's lecture today, Reflections on the Beginning and End of Everything, is itself a kind of theological provocation. It invites us to ponder the creation and destiny of the cosmos, the ultimate questions of origin and purpose that have occupied philosophers and theologians pretty much forever. At the Divinity School, we take special interest in these kinds of crossings, where cosmology meets metaphysics, where scientific discovery brushes up against moral imagination. This is, after all, the very heart of what we do here, to explore the human search for meaning across traditions, times, and disciplines. In the medieval world, thinkers such as Maimonides, who we had the pleasure of discussing, Ibn Rushd, Averroes, and Aquinas tried to hold together the knowledge of their age, astronomy and theology, physics and ethics, believing that truth, however discovered, ultimately coheres. Professor Holtz continues in that tradition, though with modern tools and cosmic data unimaginable to those earlier seekers. His reflections on the beginning and end of everything remind us that our intellectual curiosity is itself a form of wonder, a recognition that the universe, vast as it is, remains deeply connected to the moral and spiritual questions of our own survival. With this, I invite you to join me in welcoming Professor Daniel Holtz.
Hi, everyone. So I'm Daniel, and thanks for that kind introduction. As Kim mentioned, I'm a physicist. I work mostly on black holes and gravitational waves. In fact, this morning, we announced a LIGO discovery of 2 new binary black hole systems. They're pretty interesting, very suggestive. Various properties of those systems indicate that the black holes that we're detecting were themselves made out of smaller black holes in what we call hierarchical formation. It's a big deal if it's really true. It's just the first hints of this. We're really excited about it. That's kind of my day job. I'm not going to be talking about those sorts of things here. I'm going to be kind of focusing more broadly on some questions that I hope will be of interest to you all. So here's my outline. This is kind of the plan for the talk. I'm going to try to tell you 3 stories, and then I'll conclude. And the stories kind of concern different scales, and I hope that you'll see that there's some connections between them. So that's the plan, and I'm going to start with the first story. Okay, and the first story is cosmology. In my first version of this talk, the talk just became a primer on cosmology, which I'm still excited to give if anybody wants that. But I've changed things to try to distill what I think are some of the more interesting things that come out of cosmology. Some of the kind of things you learn as a practicing cosmologist. There are these kind of understandings I have, which I haven't really articulated before in this talk. So thank you. This talk has given me a chance to kind of try to think those through and try to explore how those might connect to other things that I work on and other things that people might think about. And so when you talk about cosmology, there's been this pretty dramatic evolution in our understanding of what the universe is. This place that we all live. What is it in terms of time scales, in terms of length scales? And so what I'm going to do in story 1 is try to give you some sense of that. And I'm going to do that just by kind of exploring how our understanding of those scales has evolved. And so I think probably most kids, when you first start, there's this idea that the Earth is the center of the universe, and that's extremely reasonable. And I as a physicist doing history, so beware. But my guess is that for thousands of years, people thought that the Earth was the center of everything, the center of the universe, like literally the center of the universe. This is the geocentric model. Everything revolves around the Earth, including the sun. Okay. Even to just suggest that maybe that wasn't the right picture, at some time was incredibly radical and subversive, could get people, burned at the stake or other dire consequences of just entertaining the notion that maybe the Earth isn't the center of everything. And I think that alone is also an interesting conversation about cosmology and kind of the radical nature of cosmology when you really kind of take on board some of the things that come out of our physical understanding of cosmology. It does make statements about, obviously, literally our place in the universe, but also our conception of ourselves. And I think that's kind of a running theme. Needless to say, the geocentric model, not a great description of our universe, so that, was replaced. So no more geocentric. Heliocentric model was the next obvious step, and that is a much bigger universe than just the Earth and the sky. Now, you're in our units, you're 8 light minutes away. You've really exploded what we think of as the universe. This is a very powerful model, but what was realized actually pretty early is that in this model, once you displace the Earth from the center and allow the Earth to be orbiting a star, the sun, you realize that maybe these other points of light are just other suns, like our sun, just very far away. And that model is a huge leap. So the next model after the heliocentric model involves a leap of factors of roughly 1 billion, which is an extremely large number. You're going to hear me say 1 billion quite a few times in this talk. This is one of the themes, is that the scales that we're talking about are extraordinary. So the heliocentric model, the Earth goes around the sun, not a great model. That's now also replaced. Now we'll move on to much bigger scales. So once you're in this next step, you say, okay, the other stars, they're just far away, but otherwise they're kind of like our sun. And one thing you learn as you observe all these stars is that, first of all, there are a lot of stars. There are a lot of stars on the sky that you can see with your naked eye. If you have a telescope, there are a lot more. There are billions of stars just in our Milky Way. And they come in all shapes and sizes. And as you study them and you compare them to our sun, one thing you learn is that our sun is not an unusual star. It's a very common star. It's not a particularly exciting. There are some stars that are much bigger, they're much more interesting for various reasons. There might be stars with very low metallicity. There are all these properties of stars that you can get excited about. Our star is just kind of normal. That's just one of those things. Our sun is average. Okay. I mean, not a value judgment. I'm just laying it out there. Okay. Another thing you learn is that the Earth or our solar system is not actually at the center of the Milky Way. Now, you've already blown up your conception. It's not that the universe is the sun and planets going around the sun. Okay, we're part of a much bigger assemblage of stars, which we'll call the Milky Way galaxy. And you've probably seen pictures like this. This is a picture, if you're in the southern hemisphere and you look up at the sky, this is the kind of milky thing that we call the Milky Way, which is our galaxy. And that's just a bunch of stars. And the fact that it looks like that immediately tells you that we're not in the middle of it. Because if we were in the middle of that, the sky would look the same in all directions because we'd just see stars everywhere. But we're actually way out on the edge, and so we see it as this projected line. Okay? So already, I mean, a lot of you are nodding. It's kind of obvious to us now. Would all be burned at the stake if we had said this some number of hundreds of years ago. The idea that we're part of this massive galaxy and that we're nowhere near the center. We're not even, I used to say we're in the suburbs, but we're really not in the suburbs. We're way out on the edge and just kind of a nondescript part of this galaxy. Okay. And I hope you're getting this theme. At every step, the scales are large and our place, in some sense, gets smaller. Less special. Okay. Now, that's all fine. You can have this model. We have what's called an island universe. There's the Milky Way. Okay, we're not at the center of the Milky Way. But still, that's kind of, maybe you can conceive of all that, and that makes you feel fine. And then if you have improved telescopes, you'll start noticing fuzzy blotches like this on the sky. This is the Andromeda Galaxy. So these we'll call spiral nebulae. And there was a great debate, literally a great debate, run by the National Research Council about what those fuzzy things were. Are they parts of our galaxy, the Milky Way? Are they just kind of fuzzy assemblages of stars? Or are they their own island universes? And this was finally answered by Edwin Hubble, who's a famous alum, UChicago alum. Definitely Andromeda is not within our galaxy. It's its own galaxy. It's in fact bigger than the Milky Way. And so now you have this new conception, which is not only, the universe is not centered on the Earth, the universe is not centered on the sun, the universe is not centered on our place in the Milky Way. It's not even particularly centered on the Milky Way. And this is a JWST deep field. So this is the JWST space telescope. It is just staring at some part of the sky, tiny part of the sky, much smaller than the size of the moon, at the sky area. And you just stare. And what do you see when you do that? You just see galaxies all the way down. It's just full of galaxies. Each of these little splotches, if you look carefully, is a galaxy. There's actually an incredible amount of information in this. If you kind of look carefully and think about it, not only do you see that there are galaxies everywhere, but the smaller galaxies have a tendency to be more red. That's a hint that the universe is actually expanding, which then gives you yet another sense of the scale and the fact that the universe has not been around forever. So there's a lot there, and I'll talk a little more about this. But again, here, just this jump, when you get a picture like this and see all these galaxies, this is a jump of another factor of 1 billion. So that's 1 billion times, it's not 2 billion, that's 1 billion times 1 billion. That's an extraordinarily large number. The universe is really, really big. And we're just in some kind of random part of it. Okay, as if that's not enough, the Milky Way itself, not a particularly exciting galaxy. Pretty typical galaxy. It actually is slightly atypical. The supermassive black hole at the center is pretty wimpy. Okay. But there's nothing, there are lots of galaxies that are kind of exciting. They can be very massive. There can be parts of galaxy clusters. There can be a lot of star formation going on, which is a sign of what we consider active galaxies, lots of activity. They're galaxies that have these huge radio lobes and jets emanating from them. Our galaxy doesn't really do any of that. It's pretty boring. But that's our galaxy. That's the Milky Way. All right. You might be thinking, okay, this is all fun on the cosmological scales. You know, you're probably getting this point. We're not particularly unique or special. But if you kind of look closer to home, we have these planets, you know, orbiting the sun. And maybe that's kind of unusual. And you could, people discuss this 20 years ago. This would just be an abstract debate. Are we unusual or not? We didn't really know. But in the last decade or so, we've started to have telescopes that can detect planets around other stars. These are called exoplanets. And they're all over the place. Basically, all stars have planets. Every time you look long enough, you find a new, solar system set of exoplanets. Planets are extraordinarily common. Something we didn't know before, but now it's true. So that is not something that makes us special. Well, you might say, well, okay, planets are common. If you actually kind of went and analyze it, these are pretty big planets. They don't look long. It's much easier to see a big planet than a small planet for various reasons. So we detect big ones. But if you get more and more sensitive, you start to detect the small ones. And it turns out actually there are plenty of planets just like the Earth, which is just one system. And in fact, there are plenty of planets that are in what we call the habitable zone, where they might harbor life. This is a little more controversial. We don't have that much data yet. This is kind of active work in progress. A lot of my astronomer colleagues focus on exoplanets. It's very exciting. We're starting to be able to measure atmospheres. A lot of activity. Bottom line, as far as we know so far, does not look like the Earth is that unusual in terms of planetary properties. We'll see. This is still kind of in progress. Okay. All right. Just to really hammer it home, so the universe is really big, tons of planets around tons of stars, in tons of galaxies all over the universe. But the universe is also evolving, something we can talk about, and I kind of alluded to that with this picture, but the universe has been changing with time, and there was a Big Bang, and very happy to talk more, answer questions about that afterwards. But one of the things we've learned about the universe is that it does change, and that it started in this very sort of pristine state and has evolved since then. And as it was evolving, lots of things happened. The first stars were born, they lived, they died, they exploded in these massive supernovae and enriched the elements. And then you had another generation of stars, and all these things, galaxies are colliding. Very exciting early years of the universe. Teenage years were amazing. We're now 14 billion years in, and the universe is actually pretty boring, comparatively speaking. There's less stars are being made. The peak of star formation was, maybe 10 billion years ago. That's relevant to black holes when you study black holes, because that's when most of the black holes were made, we think. That's one of the things we're studying. A lot more galaxy collisions in the early universe. Just a lot more stuff happening. Right now, kind of boring. I mean, there was also this kind of interesting moment when the universe transitioned from dark matter to dark energy, something I'm not really talking about, but you can ask me about it. Again, that happened a long time ago. Now, the universe is kind of just doing its thing. We don't live at a particularly special time. Okay. This is all a very long-winded way to talk about the Copernican principle, which is something we talk about a lot in cosmology. Like a lot of principles in physics, it's not that well defined, and we use it in way we kind of evoke it just as a kind of general feeling of something that's helpful to frame our thinking. And so the Copernican principle in this case is something like we're not in a privileged place in the universe, which is to say, we think if you happen to plop down our solar system in some other part of the Milky Way or some other galaxy somewhere else, everything would look pretty much the same. There's nothing that special about where we are here right now. Okay, that's kind of a principle, and it's, from what we can tell, that is the universe satisfies this principle. There's a kind of stronger version called the mediocrity principle, which is basically we're just not that special, which is kind of, another, there are some distinctions here, and I'll kind of get into those distinctions as we go along. But, to kind of summarize story number one, geocentrism, no. Heliocentrism, no. Galactocentrism, which is our galaxy is the center of the universe, no. Cosmocentrism, which was a word I made up for this talk. Then I Googled it, and of course someone else has made it, but it's not clear what they're referring to. This is my version of there is one universe. And even that, some physicists would argue, there's this big fashion now of multiverses. Maybe there are 10 to the 500 universes. All of them have their own laws of physics. We just happen to be in one, and ours isn't particularly special. I am not going to go there, but okay, that's something you could talk about. The real question here is this final question, which is anthropocentrism, which this is how Google defines it, which is this belief that humans are somehow very important and special. And so despite all this stuff from the physical world that says we're just in some kind of random part of the universe of no particular distinction, there's something very important about us here on Earth. And I'm not sure what to do with that, so I'm just going to go to story number two. But I think it's something we should keep in mind, and we can discuss after it at more length. Story number two definitely connects to this, which is this question of is life, is humanity somehow important? So let me go to story number two. All right, how am I doing so far? People, okay, I'm getting nods. If you have a burning question, you can interrupt me. I'm happy to engage. All right. So I'm going to start. So this is story number two. And it starts with Enrico Fermi, who is a faculty member here, had his career here, and I'll talk more about him later. Walking to lunch, he's visiting Los Alamos, and he's walking to lunch with a bunch of colleagues. I'm pretty sure this is a real story, not apocryphal. They're walking to lunch, and they're discussing this New Yorker cartoon, which had just appeared. And for those that can't see, the New Yorker cartoon is a bunch of aliens with New York City trash cans. They're stealing the trash cans. I'm assuming that there was something going on in New York City and people were stealing trash cans. I don't know. Anyway, they're discussing this. They're walking to lunch, and Fermi asks, Fermi asks the following question. And I'm just going to quick aside. So Enrico Fermi is legendary within the kind of scientific community because he was a preeminent theorist and a preeminent experimenter. He just had this facility to do everything. And this is one of these examples. He's also famous for Fermi estimation problems, which some of you may have heard of. This is the Fermi paradox. It's just one of the things he just kind of spun off, which is this question, where is everybody? Which at first kind of sounds like a joke. But, the question is a very meaningful question, which is, I've told you, and the whole first story was sort of predicated on this idea, we're not special. And if we're not special, then there must be lots of other civilizations out there on other planets around other stars, just like us, maybe much more advanced than we are. And if that's the case, why don't we see them? Why aren't they visiting? I mean, that's a real question. So we don't know the answer to that. They certainly didn't know the answer to that. So what physicists do when you have no clue is you just write down an equation, and then you just hope for the best. And so Frank Drake wrote down this equation in 1960, I think, which is, this is his version of where is everybody, trying to answer that question. Okay? And I know I'm not supposed to be showing equations, but it's not even really an equation. And I'm going to kind of walk through what you can think of as a kind of this heuristic. And I'm going to walk through the heuristic with you. But the goal is to kind of estimate the number of active, technologically advanced civilizations in the Milky Way. So basically, where are the aliens? If life is common, where are they? And this is how you would estimate it. And just, even though I will say there's a lot of back and forth and controversy is strong, but there are many scientists that think that this equation is, or used to think that it was just ridiculous because we didn't know anything about it. And therefore, it was all just hand-wavy nonsense, and you could get whatever number you wanted out of it. And as I'll explain, actually, I think that the feeling associated with this equation has been shifting, and we'll go through it. And the main thing is that we're starting to actually nail down some of the aspects of this equation. And that is very exciting and kind of shocking. But there's still huge uncertainties, and I think the last term is the one I really want to focus on. So I'm just going to kind of step through some of the aspects of this equation. Okay. So what are we calculating? We're just trying to estimate the number of advanced civilizations in the Milky Way. So that's the question of, where are they? If there are a bunch of advanced civilizations, they should be visiting us. So why, what is that number? Is it 1, like us, or is it 10 to the 9, in which case they're everywhere? Okay. So that's what we're trying to calculate. If you think about what it takes to have an advanced civilization, there are just a few steps you have to get through. First question, you probably need stars to have an advanced civilization. All the energy on Earth, what keeps us alive, what powers everything about our lives, originates in stars. We need a star. If you don't have any stars, you're probably not going to have any civilization. So you just start with, well, how many stars are there? Okay, that seems pretty straightforward. Then you want to know, how many of those stars have planets? Now, this used to just be completely made up. I mean, you could put whatever number you wanted because we had no data. Now we have data. We can tell you, basically all the stars have planets. Then you can say, well, okay, that's fine. You have a lot of planets. How many of those planets are suitable for life? What do you mean by life? A little tricky, suitable, and it gets it's not rigid, but you can get some sense of how common is it to have a planet which would be able to harbor some kind of life. Okay, now we have some estimates of that too. It's relatively common. All right, so all these numbers are actually pretty high, this set of numbers. Okay, the next set of numbers, much trickier. Okay, you have a planet that has the possibility of life, but how many, what fraction of those planets actually generate? And that, we don't know. There's a whole Origin of Life Institute here. It's sort of one of the preeminent places where people are trying to figure out how common is life? What does it take to generate life if you start with a planet that has no life? And we still don't really know the answer to that. Then you can ask, okay, let's assume you have life, but it's probably, simple life. How likely is it that you not only have life, but the life ends up with, intelligent life? have to define that too, but, life that can build things, construct things, harness the power of the atom, launch things into space. How likely is that? We don't really know, but that's something that you want to estimate. And then there's this final question of those, what fraction then interstellar, start sending probes on, would come and visit Earth or communicate with us in some way. And we don't know that either. So these terms, we just don't know. Now, I can give, if you remember my first story 1, basically, the message is we don't seem to be that exceptional. So if you take that over to story 2, I would say it's unlikely that we're the only ones that have gone through all of this, but that is just me opining. Some of my colleagues would vehemently disagree. Their papers kind of published on both sides. We don't know. I'm still going to hold, I would be shocked if all of these are zero. It just doesn't happen, or it's only happened once in the entire universe. But we can talk more about that. Okay, there's one more term. And this is the last term, which is, fine, you get to be an advanced civilization. You can send probes out into space. Maybe you can send a probe to the nearest star or the nearest planetary system. That's really exciting. The question is, how long does the civilization last? Because even just the Milky Way is big. If you went at the speed of light, it would take 30,000 years as measured by us here for you to get anywhere, to get towards the center. So it's tens of thousands of years at the speed of light, and you don't get to go at the speed of light. So for any kind of realistic near-term expectation, you're probably talking about 100,000 years or 1 million years to kind of really get out into the galaxy. On the time scale of 1 million years, if we last 1 million years, I don't think, lots of speculation, but if you kind of look at the pace of our technology just over the last 100 years, and you shoot that forward 1 million years, I think it's not crazy that we'll have explored a lot of the galaxy. We'll have sent probes everywhere. If there was some other, planet with people like that sitting on it, we might have contacted them. Or in other words, if there are lots of civilizations and they last a long time, they should be here. So this question of where are they is a really important and relevant question. Go ahead. Just one aside on this, I've assumed, implicit in Fermi's question, and implicit in what I'm saying here, is that no intelligent alien visitors have come to Earth, which, okay, we can discuss, but I think that's what's called Thought Day, and I'm happy to take for granted, and we can discuss after. I'll just point out, many of these terms that I was just talking about, these numbers are huge. The number of stars in the Milky Way, the number of planets in the Milky Way, this is a number on the order of tens of billions. These are very, very large numbers, which leads to something called the Great Filter. The fact that there aren't aliens all over the place tells you that one of those terms in the whole series of terms, at least one of those, is a tiny, tiny number. There must be some point which cuts off the ability for other life to exist and send probes to us. And so because that we have observed that it does not seem like our section of the galaxy is teeming with alien life. There are other experiments, but this is in the context of the Drake equation. That's the thing. So one number is small, and you can ask basically which number is it. So the end of story number 2 is in the context of one number is small. I'll just point out that that last term, if you think about where we are as human beings right now, that last term could be actually at least for us, pretty short. And so now I get to the Doomsday Clock. Sorry, I'm going to try to be more hopeful towards the end, but this was on my first slide, so you kind of knew where I was headed. So now let's talk about the present. So, okay. And so to do this, I talked a little bit about length scales, and I'll just talk a little bit, it's the Doomsday Clock, so I should talk about time scales as well. So here's just some relevant time scales. These are all very rough, but it just to get you kind of oriented. Okay, the universe, it's been around roughly 14 billion years. Pretty long time. The Earth has been a respectable fraction of that. The Earth has been around, and some sort of life on Earth, also a good fraction of the Earth's history. The first kind of human beings, broadly defined, probably a couple million years, which is a long time by our standards, but very short in terms of the history of the universe. Homo sapiens, it's hundreds of thousands of years. Hey, that's actually quite recent. Civilization, it depends how you define it, on the order of 10,000 years, maybe 100,000 years. Is it the first time you have writing, or there are different ways to do this, but it's on that order. Okay. We've been burning fossil fuels for energy a few hundred years. Nuclear weapons, we've had almost exactly 80 years. AI, maybe 5 years. Okay. These are the timescales that are relevant. Part of my theme is going to be these, especially these last two. This is extremely recent. These are the ones where we get to, screw ourselves, as it were. And that we've only had that power very, very recently, especially in the history of the universe. Okay. Another aside, this is a good place to be having this discussion, because Chicago really is, in some sense, the home of these sorts of discussions. So the birth of the nuclear age happened just a few blocks that way. At this Henry Moore statue, that's literally the place where there was the first controlled nuclear reaction by Enrico Fermi and his team. That was the birth of this age we're in now, this nuclear age. And that happened, just over 80 years ago. Also, interestingly, the birth of arms control and concerns about existential risk, that also happened by those same scientists at the same time. In fact, even before the Trinity test, this is June 1945, a bunch of scientists wrote a document saying, we're freaked out. We're very worried about this new technology. And they had a bunch of recommendations. We should, be very careful about controlling it. We should do a demonstration of the technology first before ever using it in war. There were all these things. They had a whole, we need to be responsible and think carefully about this, because this is super dangerous. And this could be a problem for all of humanity. That was called the Frank Report by James Frank. There's a James Frank Institute here on campus. Totally ignored. Not clear it went really anywhere, but did kind of lay the groundwork for these sorts of efforts. And of course, the Bulletin of the Atomic Scientist was founded here on campus. And so I'm going to talk a little bit about that just to get everyone oriented. The main point here is that these technological advances, bring some amount of danger. It was one thing when you invented the bow and arrow. It's a completely different thing when you're harnessing the power of the atom. And once you're doing that, you have this kind of new power. And the question is, how does humanity handle it? And I just find this was a fundraising letter by Albert Einstein for the Bulletin. He was, the founding member of the board of sponsors. And this was his quote. You've probably heard this version of the quote. All this stuff is quite early. This is before it's really apparent to most people that we might be in trouble, because this is before hydrogen bombs, before a lot of the things that we really worry about now. Even then, people were alarmed. Okay. So I just spend a few minutes talking about the Bulletin of the Atomic Scientists. So this is this organization founded on campus by Manhattan Project scientists, scientists who helped do CP1 and who worked on the Bomb Project. And there are many, from the scientific perspective, like these are all legendary scientists. Many of them were at Chicago. And the mission was pretty straightforward, which is, these technological advances are sort of dual use is the kind of term people like to use. They can be used for good or for bad, and let's try to use them for good. So that was 1945. This organization was founded in 1947, and one of the points of the organization was scientists who are kind of experts on these technology are going to inform the public and policymakers about issues associated with the technology. That was part of the goal. And so they kind of produced an actual bulletin, a magazine, and the magazine needed a cover, and so this was the cover. And that's the Doomsday Clock. And it was set just arbitrarily at the start to 7 minutes to midnight, with the idea being that midnight is the end of civilization. Again, not carefully defined. It's one of these, I think we'll all know it if it shows up, but we're not going to quibble about the number of deaths or, what it means for society to collapse or things like that. And there are definitely different flavors of midnight. We can discuss that some later, but there is a notion of midnight. This is something new. This is something that we didn't have the power to bring about before about 80 years ago, but now we do. So one aspect of the Doomsday Clock, very important, is that it goes forward and back. It's not a real clock in that sense. And, the way I always phrase it is, it's really a symbol of hope. The whole point of the Doomsday Clock is a hopeful message, which is we can turn the clock back. And so it's to kind of convey that we should be alarmed, that there are these concerns, there are these profound issues, challenges, but there are actions we can take to turn the clock. Okay, so the question is, what time is it on the clock? And Jim already told you, it's now 89 seconds to midnight. We announced that in January, and that is indeed the closest we've ever been to midnight. So there's this group of sort of scientists and experts. We meet a few times a year. We discuss all the things that might doom civilization, and we kind of try to get some sense of are things getting better or worse. That's our goal. We try to capture that in this one number, which is difficult to do, but we kind of work towards consensus. And we go through, and here are some of the things we're talking about, we're worried about. There's, a nuclear exchange, nuclear winter, climate change, disinformation we think of as approaching a kind of existential, it's what we call a threat multiplier. If disinformation is too rampant, then there is no acknowledgement of the other threats, and there's no hope of addressing them, and that's a problem. And then there are a bunch of disruptive technologies. Obviously, there are pandemics. There's AI. There are a bunch of things kind of on the horizon that we're so we go through all of these. There are lots of things going on in the world right now. I probably don't have to tell you that not everything is going perfectly. And that's why we're at this 89 seconds to midnight. So I could give a whole talk, many talks on all the things you could worry about, all the things that kind of determine this clock setting. I'm just going to pick one topic and spend a little time on it, just because I think it's one that is very relevant and important, but underappreciated. And I think it's important that we it's not that we shouldn't worry about these other things, but we should also, and maybe even especially, be worried about this, and that's the nuclear threat. So I'm just going to give you some facts about the current state of the nuclear threat. So first of all, there are 10,000 nuclear weapons, a little more, in the stockpiles across 9 nations. Most of those are the U.S. and Russia. These weapons, I think these weapons are not types of weapons that were used in, Trinity test or Hiroshima and Nagasaki. Those were very small. The weapons we're talking about now are hydrogen bombs, and they're easily tens or hundreds of times more powerful. So any bomb now, if a bomb were to be used, what you should have in mind is maybe 50 simultaneous Hiroshimas. That would be a small. Just to keep this in mind. These weapons are on high alert. They can be launched in a minute. And that's true for us, that's true for the Russians, also for the Chinese. Probably the French as well. Anyway, minutes. And there are reasons for that, which we can talk about. Just in case you were wondering, and you're probably already somewhat aware, there have been many, many close calls, many moments over the last 80 years, 50 years mostly, where we came very close to just having a full-on nuclear war, where individuals just happened to make the right choices, not to send the alert, not to launch the nuclear torpedo, whatever it was. There have been all these moments where things easily could have gone another way and would have very rapidly spiraled into full nuclear exchange. And then we would not be here. So we've been very lucky. And it's not just me. I mean, people that were in the room making the decisions have all said, Kennedy is on record saying, well, maybe a 1 in 2 or 1 in 3 chance of making it through the Cuban Missile Crisis. And I was optimistic because there were all these things he didn't know about threats and close calls that happened under his watch. And he, for sure, was not going to end civilization. He went into that saying, no way am I going to be the one responsible for everything. And he came unbelievably close multiple times, just by miscommunications, like not understanding the way what he was doing was being perceived by the Soviet Union at the time. Stuff is very tricky and delicate. We've been extremely lucky. Just a couple of other things. Our nuclear forces are on what's called launch on warning status. So this is a very simple statement, which is we are not going to wait to actually be attacked by nuclear weapons to send our nuclear weapons, to launch our nuclear weapons. We're going to launch them as soon as we have a warning of an attack. And there's some historical reasons for this, but it basically means if the computers say we're under attack, instead of waiting to see if we actually are under attack, instead we rush to launch our nuclear weapons. This is the system. It's also the system elsewhere. Extremely dangerous. There were sort of good reasons for that. You could argue for that maybe 30 years ago. There's no reason for this anymore, but that's still where we are. Sole authority, another thing we have, which is that our leaders, our president, the leaders of China and Russia, the individuals make the decision. No checks and balances at all. That is our system. The most important decision ever in the history of civilization is designed to be made by one person as fast as possible. No checks and balances because there's no time. I mean, there is time. It doesn't make any sense, but historically, that's where we've been at. I can talk a lot more about this. It's extremely dangerous. Needless to say, if a nuclear war happens, it's very bad. Yeah, we can talk at length about this, but there are many things that go wrong. And everyone on the planet is impacted. And I think it clearly qualifies as end of civilization. It happens very fast. If a nuclear war had started, which, again, anyone could have, it can happen for any reason. It can happen by mistake and has come very close to happening by mistake. Some computer glitch and someone launches some missiles, ICBMs, and that's all over. It happens very quickly. for our missiles to go over and for their missiles to come back, it's less than an hour. If something had happened at the beginning of my talk, the whole world would be over by now. That's what we're talking about. This is a movie that just came out. You can stream it on Netflix. Catherine Bigelow movie. I think it's really good to capture some of this. It came out, I think, last Friday. And it's also screening downtown Chicago, if you're interested. Anyway, that's just one example. There are lots of other examples. We can talk about climate change or AI or all these other things. These are the sorts of things we worry about with the Doomsday Clock. These are things that we think everyone should be worried about. The good news is that there's plenty that can be done. And so this is now just a plug for the Existential Risk Lab, which Jim mentioned. What he didn't mention is he's on the faculty advisory board, as is Luis Benencourt, who's here in the front row. This is an effort to develop kind of a program on existential risk. These are, we think, kind of important issues. If you're a student and you want to learn about existential risk and maybe make a difference, you can't major in it anywhere. There just isn't really an academic program for you yet. So we're trying to build one, and we have lots of activities on campus. We have research groups. We have a very active summer research fellowship program. There are a couple of fellows in the audience. We do public lectures. We actually did a movie screening of House of Dynamite a couple of weeks ago, downtown Chicago. I teach a class with James Evans called Are We Doomed? And one other thing we did, which is relevant, I think, is that we ran this thing called the Nobel Laureate Assembly for the Prevention of Nuclear War. We brought a bunch of laureates, nuclear experts to campus this past summer and came up with 14 recommendations. Here are things that can be done, very practical, short-term recommendations that would decrease the risk of nuclear war. 129 laureates have signed up these set of recommendations, and we presented it to the United Nations, and we're doing all this work with that. The main thing is it's actually pretty straightforward in some sense. We know the things we could do. No one wants to blow up the world. So the reason that we're in these weird things where it's particularly dangerous really don't make sense. And people acknowledge that, but somehow getting to where we need to be is hard. And so this is part of the discussion, and I can talk a lot more about that. Okay. That's it for my third story. I'm just going to kind of wrap up, and then there'll be some time for questions. So, there are a number of different things going on here. And my first story was all about sort of this decentering of humanity, that as we learn about cosmology, as we learn about the physical universe, physical cosmology, our place becomes, we're not the center of everything. And by that, I mean, to the tune of 1 part in 10 to the 18, like this huge number of insignificance, if you like. So that's just what we learn from physics, or at least that's one of the things I take away. But on the other hand, the Doomsday Clock does center humanity. It is, we're our greatest threat. And I think there's something, interesting about that. While I made this huge argument that we're not special and we don't live at a special time, the Doomsday Clock says, actually, we are special. We live at the time where we first have the power to destroy ourselves. We've only just really gotten that power in the last 50 or 100 years. So this is a very unique time in the history of humanity, in the history of our civilization, because the question of whether we go on for millions of years or whether we don't make it through the next century, that we're going to answer that one way or the other pretty soon. Like in the next 100 years, we'll know whether we're going to make it 100 years. So this is a kind of unique time. And what's interesting about this, and I think hopeful, is it really is in our own hands. Like, yes, I mean, the universe is not out there watching out for us and making sure. The universe really won't notice if we blow ourselves up. It's just not the way things are structured. But but we'll notice, and we have complete control. And the threats are our own threats. It would be completely different if it turns out that, an asteroid is going to take us out, and that happens every 10 million years, and there's really not much we can do about it. Or really, if it happened every 100 years, but then we wouldn't have gone where you could imagine natural things happening that would be threats to us. Those things could happen. A black hole could wander nearby, and I even wrote a paper about that. It's extremely unlikely. It's not something we have to worry about. This other stuff we do have to worry about. And so, okay, we can worry about it, but we can also we have complete control over that stuff. And that's very empowering. And so, kind of the hope after all of this is that you come out feeling like, okay, there are these threats. It's a dangerous time, but it's all in our hands. There are clear things we can do. We just need to kind of do those things. I will end there. And so the question was, how was it set during the Cuban Missile Crisis? And what happened, so one thing I should clarify about the Doomsday Clock is it's not a real-time clock, in the sense that we don't kind of monitor the tweets and like, oh my God, this was tweeted, now we have to adjust the clock. We try to kind of integrate out over a little period of time and try to really understand what the threats are. During the Cuban Missile Crisis, there was a lot of chaos. People did not have full information, did not really know what was going on. By the time the clock was set, after the Cuban Missile Crisis, it went back to 7 minutes to midnight. And the reason for that was because people had gotten so freaked out during the Cuban Missile Crisis that there were all these positive steps. There was much better communication, the establishment of the red phones and a lot more trust-building exercises, stockpile, conversations about managing the stockpiles. Things got actually demonstrably better. And so, during, it would have been impossible to set the clock during the crisis because we just not everything was classified. We had no idea what was really happening. Yeah, so the question is lessons from the last 80 years in terms of all these close calls and just advances of technology. So there's one lesson that I think is now kind of taken on board by most people, which is when people practice, when they do war game scenarios, one thing that is found essentially universally is as soon as nuclear weapons are used, it rapidly spirals out of control, it escalates, and then all the weapons are used. And in scenarios where there is pressure to use nuclear weapon, like there's a scenario, actually the movie shows one, but there are many cases where a leader might consider using nuclear weapons. Often the establishment around the leader pressures the leader to use nuclear weapons. And so we can talk about that. There's a lot of weird psychological stuff that happens that makes it much more likely that nuclear weapons are used. And once they're used, it makes it much more likely that all the weapons are used. So we can talk about that. In terms of just the basic, what are the things that can go wrong? There are a lot of things. For many years, the way the nuclear forces were deployed is there were a bunch of Air Force pilots that had access to nuclear weapons with essentially no controls, and they were able to fly off and deliver those weapons. And that was the system because it had to all happen very quickly. And so they would practice loading these weapons onto the plane and flying off, armed, ready to go, and then coming back and landing. If any one of those pilots had decided, I'm just going to go and hit my target, that would have been it. Because, as I just argued, as soon as one of the weapons is used, if someone were to go fly to Moscow and nuke them, that would be it for everyone. So there were actually many hundreds of people that could have ended civilization. That makes no sense. That has gotten much better. Now there are all sorts of controls on the weapons. It's not that easy to launch a weapon, in a rogue sense. But the overall structure, launch-on warning, solar authority, that stuff, we're still kind of in the Stone Ages. We just haven't been able to move through that. And there are various reasons for that. And so, none of the reasons are good, but that's where we are. Yeah. So I guess the question is, how does the clock respond to kind of leadership in various offices? And that's tricky. I mean, we don't. The way we set the clock is we look at what is actually happening. Like how are people talking, engaging with the world? Like are countries engaging to reduce the risk or increase the risk? What's happening to the stockpiles? There are a lot of questions we ask. And so personality is part of this in the sense that there are some leaders that you think may be more calm and kind of collected about using nuclear weapons or, for example, engaging with climate change or any of the other threats, and other leaders that don't. And that's something you have to factor in. I will point out that the Doomsday Clock, we care about civilization, everyone. And so we look at everyone. And so it's not just the U.S. It's really, it's a big world out there, and we try to incorporate what kind of the state of the entire world into our decisions. I know it's not a perfect answer, but that's where we are. Yeah, I mean, and it's very hard to know what the actual impact is. Yeah, so that's a really good question. So the question is, how do we create public movements? And, one of the things we talk about is we need public movements. And there have been public movements in the past. There were ban the bomb movements, for example, on the nuclear side. There have been cases where the public kind of mobilizes and pushes for change. How you make that happen is a much harder question. Many of the historical movements where you had millions of people marching in the streets took real work for many years of people developing awareness, mobilizing, self-organizing. It's not something that just happens all of a sudden. The question of how we make that happen again, I don't think there's a simple answer. I think part of it is students need to be informed and engaged. And basically the entire generation, the younger generation, needs to get out there and, get involved somehow. And there are many ways to do that. Part of it is marching, but part of it is voting. Part of it is just working on these issues in however you can. Talking to your friends, like going door to door and canvassing. There are lots of ways to get engaged. We need to do all those things. That's kind of the short version. But I don't have, and it's one of the things we're hoping to kind of spur discussion about is what are the best ways to make change? And that's just a very complicated question. It depends a lot individual by individual. Yeah. Okay. So I'm not familiar with this particular object. I am familiar with the general discussion about, with objects from out of our solar system passing through, which is something that happens. And, I know Avi Loeb, I chatted with him about this. Avi Loeb, for those that don't know, is a professor at Harvard, and he's gotten very excited about the possibility that some of these objects, so there are objects kind of wandering into our solar system all the time. There's kind of an asteroid belt, and then some of them come from farther, and kind of from the direction they're coming, they clearly are just from outside. And he has said maybe some of these are, alien probes, which is an extremely exciting and obviously extremely provocative statement. And he's written some books and gotten a lot of attention for it. Avi definitely is an extremely talented, astrophysicist. He does a bunch of calculations and says, here's why I think this might be interesting. in most of those cases, then there's been follow-up, and either the data isn't good enough, or arguments are found that basically say that's pretty unlikely. And that's been kind of a pattern. And I think, this sounds like one of these cases where, it's probably normal. I would have to look at the data. I haven't heard anything that people are particularly excited about whatever this is. So chances are it mostly exists on YouTube and not in, the community. But, that, I think what you're talking about is absolutely relevant, which is probably we should be aware of those discussions. We should try to kind of engage with those discussions. There are things that we are excited about. I mean, there are these black holes that's real. It's really exciting. It tells us something about how the universe makes black holes. Black holes are extremely important fundamental objects in the universe. So I'd love for there to be YouTube videos about that. But, they're probably aren't. So, it's one of these things that I think you're right to kind of highlight this as something that needs to be discussed. But again, I think it's a similar theme. I'm not sure what the next step is. Yeah, so there's a, very interesting question of, and people talk about this, can we think about the universe as an information processing system instead of, a physical system? And there are ways to do that and express it, and a lot of the questions in sort of fundamental physics, you can ask that way. Black holes, just so happens, are a very interesting part of that conversation, and what happens to information in black holes is maybe one of the greatest mysteries in physics. So all of that, I think, is worth thinking about. I don't think any of that changes our understanding of where we are here now in terms of, we don't seem to be in a particularly rich information environment compared to many other places. Yeah, so that's a very good question for those that... Could you hear it on that side? Yeah, oh, great. Okay, so the simple answer is we don't quantify. It's very hard to do. We're trying to come up with ways to kind of, capture the way these things interact, but it's very hard, as you said. So, how disinformation impacts political decision-making is, we don't know. I mean, it seems bad, whatever it is, but exactly how bad, and as the disinformation gets worse, how do we quantify how much riskier it gets? That's very hard to do. So what we can do is kind of capture the sense that, things seem more unstable, and the way people talk about it, the decisions that are being made, that we see actual decisions being made, the way politicians interact, the way foreign policy works. There you can actually look at things on the ground. For example, do we have new treaties governing nuclear weapons? The answer is no. The fact that that's the case is something we can act on. The last treaty expires in February. That's New START. Then for the first time in more than half a century, there will be no controls on the number of nuclear weapons, period. It's completely nuts, but that's what's happening. So that we can act on. And so that's kind of how we do it. But would love to kind of be more sophisticated about it. It's just very hard, and it's also changing all the time. Yeah, so we have a great example of this right now, which is AI. So there's a lot of discussion about AI. The practitioners of AI, some of them are saying we should all be really worried. This is an extremely dangerous technology. It could threaten all of humanity. There's some very prominent people that say we should just stop. This is completely irresponsible. At the very least, we should have guardrails. We should be deliberate. And then there's a whole group. It's like, this is an arms race. If we don't win, China will win, and then we'll be destroyed economically, but also just destroyed because whoever has the best AI wins at everything. And it's literally being presented as an arms race. Right now, the arms race people are for sure dominating the conversation. And all the kind of, I think even just today, there was like OpenAI is now restructured to be pure for-profit arms race type company, even though it was meant to be an AI safety company when it was founded. So that's where we're headed. That's an example. There's been a lot of talk. There's been activity. There have been various regulation proposed. It's even the stuff that's been proposed, and some of it was put into practice. Europe has actually been really ahead of the game on this. That stuff is insufficient, but at least they're trying. It's going to have very low impact because right now everyone is racing ahead. So, that's worrisome. Now, whether or not it really will spell doom, we don't know. And I think there's a lot of uncertainty there, but for sure, we're not doing the very kind of sensible steps of maybe just taking a deep breath and making sure we're going to be okay. So that's a way to say what you're asking for is clearly not happening. Probably should. Again, it will take, unfortunately, there's so much money involved that it's very hard to kind of counter that with a common sense message. But we have to try. The one thing for sure is there's a lot of discussion about it. There's a lot of awareness. That's good. And this easily could be happening with no awareness. And, I don't think we're there. So part of the message is happening. You're just not fully there. Yeah. So the question was, eliminating nuclear weapons. So there's something called the TPNW, which is the Treaty on the Prohibition of Nuclear Weapons. There's a goal. And interestingly enough, many nations have committed to this goal of having no nuclear weapons at all. And even as part of the Non-Proliferation Treaty, there's this abstract ideal that even the nuclear states are saying, yes, the goal is to reduce the number and eventually eliminate nuclear weapons. Like, these are not reasonable things for us to help. So there's a lot of talk about that as a long-term goal. The question of whether we need to take steps along the way is actually something that we discussed, and we had this, Nobel Laureate Assembly, and it was one of the things we discussed at some length. There are some people that think we should just push for zero now. Everyone should just mothball their weapons, dismantle them. That is the next step. And anything short of that is failure. And then there's another community which says, well, we used to have 60,000 plus nuclear weapons. We now have 10,000. Let's get it down to, in the world, let's get it down to 5,000, then 2,000. Like, what is the minimal deterrent? What is the minimal number of nuclear weapons you need to convince someone never to mess with you? And that number is definitely less than the number we have now. And so you can imagine some people find that really just an awful discussion to have, and we should just go to zero. And others are like, that's the practical question, and let's just try to get there. One thing I think everyone agrees on, except maybe the military industrial complexes, less weapons is better. Like, we don't need thousands. Like, that's not making us safer. It's definitely making us less safe. And so kind of, at least my personal view is, at the very least, let's reduce the number of weapons. For context, right now, as I mentioned, we're probably on the verge of a new arms race where we're going to increase the number of weapons and we're going to make them more powerful and better, even though they're already really, there's no functional way to improve them. Anyway, so we're not headed where we probably want to go. So I understand that feeling, and I mean, to be honest, I often feel that way. Oh yeah, who's really listening and what? But it is the case. I mean, and this is what I do hold on to. It is clearly better for all of us to take these steps. I mean, that I think is without. I mean, there is no opposing side, which is like, actually, nuclear war would be great, and so let's just let it happen. And that isn't a conversation you have. So there really is an opening, and it's similar with climate change. To be honest, basically everything we talk about, the things that we talk about are not that controversial. Shouldn't be that controversial. I mean, there are always some groups, but basically no one wants to have these things come to pass. So the only question is how to get that through, and it's hard. So I think what I usually tell students is whatever it is you do, like if you're an artist or you want to be a lawyer or a business person, being informed by these things and carrying that forward is helpful. And creating a generation of people that would prefer not to have the world end is helpful. And that does eventually have impact. There's no, I mean, if there were a simple like, oh, all we have to do is call this person on the phone and then they would fix everything, but we would do, it's just, I don't think it's going to work that way. But I do think that, having everyone engage will make a difference. And in many ways, that's already happening. So just because there is this, I can see this, like, I don't want to have everyone be completely despondent. We actually have made lots of progress. On the nuclear side, we did have 60,000 weapons. We were in the depths of the Cold War. Things were not good. And we pulled ourselves out of that. Part of that was mass movements. Part of that was, inspired leadership. There were many different things going on, but things got much, much better. Right? Climate, climate change is very bad. It's going to get much worse. However, you could imagine that we don't have a technological fix. It could easily be the case that the only way for us to get energy is to burn fossil fuels. And that would suck for us. It turns out, actually, we have these technologies, solar, wind. This is a problem we can solve. It didn't have to be that way, but we can. The technologies are there. In fact, the technologies are taking over. It's not happening quite fast enough. It'd be better if we were really gung-ho on that's not really going 100%. Many other nations are, for example. But it's actually overall climate. There are many ways to be hopeful about the way things are going. It could be much worse. I know that's not the and just kind of leaning into that is good. So I don't think the message is. I'm trying to say the message is not all this stuff is actually stuff we can fix, and it didn't have to be that way. There could be things we can't fix. We can fix like climate for sure. We know what the problem is. I mean, it could be mysterious. It's not mysterious. The science is pretty clear, and what we need to do is pretty clear. So, again, it's this thing of just going out and doing it, and we all do what we can.